Now look at this example. Okay, let's say an ideal diesel cycle with air as a working fluid has a compression ratio of 18 and a cutoff ratio of 2. All right. So first you need to know what is compression ratio, what is cutoff ratio. Okay. So the PV diagram of an ideal diesel cycle looks like this. So well, this is the reason why I want you to remember the PV diagram and TS diagram for every cycle so that it would be much easier for you to determine what is compression ratio, what is cutoff ratio. Okay, so the compression ratio in this case, compression ratio, I think it's R. Okay. So R is the V maximum over V minimum. So in this case, V maximum is V1, or V4. Okay, V minimum is V2. Okay, it's V2. So V1 over V2 is 18. Okay, then cutoff ratio is defined by V3 over V2. Okay, so this is a V3 over V2, and this is 2. Okay. Then at the beginning of the compression process, the working fluid is at pressure, temperature, and the volume. All these three parameters are given, and utilizing the cold air standard assumptions to determine the temperature and pressure of air at the end of each process, and network output, thermal efficiency, then MEP. Okay. All right, so very typical. So basically what you are going to do is to find out the temperature and pressure at the end of each process. Okay, so let's try this. First, initial pressure, temperature, and volume, they are given. So this is a V1, this is P1, this is P1, this is T1, and this is a V1. Okay, so initial state, it's known. Okay, then from process 1 to 2, this is isentropic process. And here says using the cold air standard assumptions. Okay, so it's ideal gas undergoing an isentropic process, then comes with constant specific heat. So we know there are three very useful equations to use, right? TV to K minus 1, this is constant. Okay, so T1, V1 to K minus 1 equals T2, V2 to K minus 1. Okay, so T1 over T2, this is V2 over V1 to K minus 1. Okay, and we know, well, this V here is the specific heat. Okay, sorry, specific volume. Okay, but the system is assumed to be executed in a efficiency in the device, which is a closed system. So the specific volume ratio will be the same as the volume ratio. Okay. So this is a V1 over V2. We know this is compression ratio. Okay. So that should be 1 over 18 to K minus 1. And K is evaluated at room temperature. Let's just say RT, room temperature, because here says using cold air standard assumption. So we can evaluate the specific heat at room temperature. So K will be a constant. Okay. All right. So P1 is known. So we have T2. Okay. Then don't forget this is ideal gas. So P1, V1 over T1 will be the same as P2, V2 over T2. Okay. Now T1, T2 are known. P1 is given, right? P1 is given here. And V1 over V2 is pressure, is compression ratio, sorry. So we have P2. Okay. Then, all right. So P2, now we know T2, P2. Now we are looking for P3, V3, but P3 equals P2. Okay. Well, if you know this diagram, then you can know this immediately, right? P3 equals P2. Okay. Then again, P2 V2 over T2. This is P3 V3 T3, right? Ideal gas equation. Okay. Then P2 is the same as P3. V2 over V3 is cutoff ratio, right? Or V3 over V2 is cutoff ratio. Okay. Then T2 is known, so we can get T3. Okay. Then again, 3 to 4 is isentropic process. So we can use T3 over T4 equals V4 over V3 to K minus 1. So we are still using this relation. Okay. All right. So this is a little bit different. Okay. Okay. So we don't know the ratio of V4 over V3. We don't know this. However, we do know is V1 over V2 is 18 and V3 over V2 is 2. So if you divide R by RC, so you would have V1 over V2, then V3 over V2. So that would be V1 over V3. Okay, but V4 equals V1. So V1 over V3 is the same as V4 over V3. Okay, so this is R over RC. So this is R over RC. Okay, then we can get T4 because T3 is none. Okay, at this moment. Okay, then P3 V3 over T3 is P4 V4 over T4. Okay, so P3, we know P3, this is P2. We know the ratio V3 to V4 or V4 to V3, whatever. Okay, then T4 and T3 is down, so we can get P4. Okay, so we have T2, P2, P3, T3, T4, P4. Okay, all right. Then the network output and thermal efficiency, right? Well, network output in this case, let's try here. Okay. Network output, so PV. Okay. This is isentropic. This is Q in. This is Q out. Right. So the network output is basically Q in minus Q out, right? And Q in, now the heat addition process is a constant pressure process, right? So this would be Cp T, I should say, well, H, yeah, this is Cp T3 minus T2, okay. And Q out is a constant volume process, right? This Q out is constant volume. This Q in is constant pressure. One is constant pressure, the other one is constant volume, okay. So this Cv T4 minus T1, okay. So this is, well, yeah, you can get Cp and Cv because Cp and Cv, they are evaluated at the room temperature. And you have all these 4 temperatures. So you can get the network output, okay. And efficiency is network output over Q in, okay. So you have network output, and this is Q in, this is Q in, okay. This is efficiency. Then finally, we are looking for the mean effective pressure, okay. Mean effective pressure is defined by the network output over the displacement volume, right? Which is the V1 minus V2. So this is MEP times V1 minus V2. Okay, so V1 is given, right? V1 is given. Okay, and V2 based on the compression ratio, V1 over V2 is 18. So V1 is given, so you can get V2. Okay, so you have V1, you have V2, so you can get MEP. Okay. Questions?
Professor, can you hear me?
Yeah.
So Cp and Cv is at room temperature because of the cold air standard assumption, right?
Yes, exactly.
Okay, thank you.
Yeah. Any other questions?
And can you show us how to find the mean effect pressure again a bit, Professor?
MEP? MEP is defined by the network output over the volume, and the maximum volume minus the minimum volume, which is the displacement volume.
Oh, thank you, Professor.
MEP times V1 minus V2, and V1 is given. V1 is given. And the compression ratio, which is V1 over V2, is given. So you can get V2. And you already have the network output. So to get MEP, just divide the network output over the displacement volume, which is V1 over V2. Sorry, V1 minus V2. Okay.
Thank you, Professor.
Any other questions? If no, then just continue. Look at this. The ideal Otto and diesel cycle are internally reversible cycles. Okay, internally reversible cycles. So involve heat transfer through a finite temperature difference during the non-isothermal heat addition and rejection processes. Okay, so their efficiencies are smaller than a Carnot cycle, because Carnot cycle is a totally reversible cycle. Otto and diesel cycles, they are just internally reversible cycles. Okay, so the thermal efficiency of an Otto or a diesel engine is less than that of a Carnot engine operating between the same temperature limits. Okay, because a Carnot engine, this is totally reversible. Okay, so Carnot engine, Carnot cycle is still the best. Okay. All right, next we are moving to Brayton cycle. So Brayton cycle can be modeled as a closed cycle by using the air standard assumption. Okay. So the Brayton cycle is actually the ideal cycle for gas turbine engines. Okay. So this is the very useful cycle, and because gas turbine engine, just like the it's like not exactly the same as the jet engine, but very similar. Okay, except the jet engine, you don't need to have the network output. But for Brayton cycle, it's gas turbine engine. So gas turbine engine is still used to produce the network output. Okay, right. So the combustion process is replaced by a constant pressure heat addition. Constant pressure heat addition. Okay, and the exhaust process is replaced by a constant pressure heat rejection. Constant pressure heat rejection. So if you remember what the PV diagram looks like for ideal Otto cycle, then ideal diesel cycle, then now we are talking about ideal Brayton cycle. So you can see the difference. For an Otto cycle, the PV diagram looks like this. Okay. So Q in is constant volume, and Q out is also constant volume. Okay, so this is Otto cycle. How about diesel cycle? Diesel cycle, the heat addition process is replaced by constant pressure process. It's constant pressure. But Q out is still constant volume. Sorry, this is Q out. Okay, so this is Q in. This is Q out. So the rate one is diesel cycle. Now Brayton cycle. Brayton cycle, the heat addition process is replaced by the constant pressure process, and the heat rejection process is also constant pressure process. Okay, so I will make the Brayton cycle like this. Okay, so this is Q in. This is Q out. So the green one is the Brayton cycle. Brayton, let me see. Yeah, Brayton. So as you can see, these three cycles, they are similar, starting with the Otto cycle. So both the heat addition and heat rejection processes are constant volume processes. Then moving to diesel cycle, you just change the heat addition process to constant pressure heat addition. Okay, and the heat rejection process remains the constant volume heat rejection. Now for Brayton cycle, both heat addition and heat rejection processes are replaced by two constant pressure processes. Okay, so these are something different among these three cycles. Okay. All right. So yeah, look at this. For Brayton cycle, both heat addition and heat rejection processes are constant pressure. Okay. So Brayton cycle, well, it's also internally reversible. Okay. Process 1 to 2 is isentropic compression. 2 to 3, constant pressure heat addition. 3 to 4, isentropic expansion. This is to produce the workout, right? And isentropic compression is work in. It's compression, right? So there's a work in. Okay. Then finally, constant pressure heat rejection process. Okay. So this is like one more difference when compared with the diesel cycle, right? Diesel cycle and Otto cycle, the only one difference is we replace the constant volume heat addition process with constant pressure heat addition process, right? If you go back to diesel cycle here, right here, the combustion process, which is heat addition process, is approximated as a constant pressure heat addition, which is the only one process where the Otto and diesel cycles differ. So we can say that the only process where the diesel and Brayton cycle differs is the heat rejection process. Okay, because in diesel cycle, the heat rejection is still constant volume, but the Brayton cycle, the heat rejection process becomes constant pressure. Okay. All right. So there's a video here. This is a very interesting and very useful actually to let you know how a real Brayton cycle works. Okay, now let's look at this video very quick.
This is the torch you use if you want to become barefoot. This is nightlight.
Air, a lot of gaseous molecules floating all around us. It's great for breathing, and it turns out it's great for getting lights turned on. That's because air, along with abundant natural gas or other fuels, are the ingredients that combine in a gas turbine to spin the generator that produces electric current. If you follow the electricity you use at home or at work back through the power lines to your local power plant, you'll see that the process most likely starts with the work of the gas turbine, the very heart of the power plant. First, air is drawn in through one end of the turbine. Then the compressor section of the turbine
This is a compression process.
Squeezed together, similar to a bicycle pump squeezing air into a tire. As the air is squeezed, it gets hotter and the pressure increases. Next, fuel is injected into the combustor where it mixes with the hot compressed air and is burned.
This is a combustion process.
Essentially, this is what happens in your family car's engine, but at about 2,900 times more horsepower. Actually, it's exactly like the turbine engines on jet airplanes. The hot gas created from the ignited mixture moves through the turbine blades, forcing them to spin at more than 3,000 RPMs. Chemical energy has now been converted into mechanical energy. The turbine then captures energy from the
expansion
gas,
process,
which causes the drive shaft, which is connected to the generator, to rotate. That generator has a large magnet surrounded by coils of copper wire. When that magnet gets rotating fast, It creates a powerful magnetic field that lines up electrons.
All right, so you can see let's see. Okay. So this is air coming in. This is air coming in. So air is compressed in a compressor. So this is compression process. So this is process 1 to 2. Then this is air fuel or just fuel. Okay. So air fuel mixture coming in to initiate the combustion process. So this is heat addition. This is heat addition. Okay. Then after that, this is the expansion, isentropic expansion. This is a turbine. This is a turbine. So the video says the turbine is actually to produce a shift work. So this is the shift. This is the shift. This one is a shift. So shaft spins, then the shaft is connected to a generator. The generator produces the real electricity. Okay. Then this is the exhaust gas. So all the exhaust gases going out. So this is the Q out, heat rejection process. So this is out. Okay, so 4 processes. So back to the slide. Okay. So Q in is combustion. Well, air is being compressed, isentropic compression. Then Q in, this is a combustion process. Then isentropic expansion is to produce the power. Okay. Then you need to reject the waste heat out of the system. Okay. Then, all right. So there's an interesting stuff here. In this diagram, you can see there's a shift connecting the compressor and turbine. So what is this? So we know compressor requires work input, right? But the turbine produces work output. So this rod, this diagram is actually to show you that some of the work output produced by the turbine is supplied to the compressor. Okay, so you can, if you make another diagram, you can see, we can say if this is a turbine, okay, so turbine produces some work, right? There's a work out. So some of this work out is supplied to the compressor, okay. Okay, and this is work in to the compressor. Okay, so that's why here we use a rod to represent this idea. Okay, so there's another ratio called back work ratio. Okay, back work ratio. So back work ratio is defined by the compressor work input over the turbine work output. Okay, so compressor work input is H2 minus H1, right? This is the compression process, 1 to 2. So this is work input to the compressor. And 3 to 4, this is the work output from the turbine. Okay, so work input to the compressor is H2 minus H1. Okay, And the turbine work out is H3 minus H4. Okay. So the back work ratio is H2 minus H1 over H3 minus H4. Yeah, here. So compressor work in is H2 minus H1. It's 1 from 1 to 2. And turbine work out is 3 to 4. So this is H3 minus H4. Okay, so that you can make sure the work input and the work out is a positive quantity. Okay, so don't forget, we always ensure that the quantity we use is a positive one. Okay, then we decide the direction. We decide it's negative or positive. Okay. So this is the back work ratio. So the turbine work out, some of the turbine work output is used to supply to the compressor. So this is the net work out. So the net work out is actually the turbine work out, turbine work out minus the compressor work in. Okay, so this is what we call net work output in this case. Okay. And again, we need to do the energy analysis or the efficiency analysis of this cycle. Okay. So for Brayton cycle, well, of course, we are neglecting the kinetic energy change and potential energy change, and we can apply the energy balance for steady flow process. Okay. So this is the energy balance for a steady flow process or device, right? It's essentially just E in dot minus E out dot equals 0, right? Then this is E in and E out. Now the energy can be transferred by heat, work, and E mass, right? Okay, and we know E mass is m dot h, right? Because we already neglect the kinetic energy and potential energy. Okay, so if you expand the energy balance equation, you would have this, right? So Q in is H3 minus H2. Q in is a constant pressure heat addition. So this is H3 minus H2. It's constant pressure. Then Q out is H4 minus H1. Okay. So Q in H3 minus H2, Q out H4 minus H1. And they are constant pressure, heat addition, and heat rejection. Okay. Then about thermal efficiency. Okay, so we know thermal efficiency is defined by the desired output over the required input. Okay, and the net work out, this is actually net work out, which is Q in minus Q out, right? So this is exactly the same as the same as the definition of the thermal efficiency for Otto cycle and diesel cycle. They are the same. Okay, so it's 1 minus Q out over Q in. Then Q out, this is Q out, this is Q in. Okay, and don't forget, we can write it like this because we apply the cold air standard assumptions. Okay, so the specific heats are evaluated or determined at the room temperature. So Cp is a constant, and Cp is a constant at room temperature. Okay, so in this case, we can kill Cp. Then we move T1 out here and T2 out here, just like what we did for the Otto cycle. Then we need to see what this is and what this is. Okay, to do that, first you need to know P2 equals P3 and P4 equals P1, because heat addition process is a constant pressure. So P2 is the same as P3, right? P2 is the same as P3. P1 is the same as P4. Okay. So P2 equals P3, P4 equals P1. Then process 1 to 2, 1 to 2 is isentropic. It's isentropic. Okay. So isentropic process, ideal gas, cold air standard assumption. So we know TV to K minus 1 is a constant. Okay, so 1 to 2 is isentropic. So T1 V1 to K minus 1 equals T2 T2 V2 to K minus 1, right? So T1 over T2 is V2 over V1 to, well, no, we are not using TV, because now what we actually know is the pressure. So we should use TP. So if you go back to check the TP relationship in chapter 7, okay. So we are going to use this TP. So we have TP 1 minus K over K, right? 1 minus K over K is a constant. So this should be T1, P1, 1 minus K over K equals T2, P2, 1 minus K over K. So T1 over T2 is P2 over P1 to 1 minus K over K. Okay. Then P2 equals P3. So P2 is the same as P3. P1 is the same as P4. This is 1 minus K over K. Okay. All right. Then because process 3 to 4 is isentropic process as well. Okay. So this follows that this should be T3 over T4. Okay, because 3 to 4 is isentropic process, so it follows this relation as well. So you would have T3 P3 1 minus K over K. This should be the same as T4 P4 1 minus K over K. Okay, then T4 over T3 is P3 over P4 1 minus K over K. Okay, so that's why we can write like this. Then we got this very important temperature ratio. Okay, T1 over T2 is the same as T4 over T3. Then if we switch T1 and T3, so you would have T3 over T1 is the sorry T3 over T2. This is T2. This is T2. Then this is T4 over T1. Okay. So just like the Otto cycle, you realize that T4 over T1 is the same as T3 over T2. So you can cancel this. Okay. So the thermal efficiency becomes 1 minus T1 over T2. Okay. And T1 over T2, T1 over T2 is T1 over T2 is P1 over P2 to K minus 1 over 1. Okay. Then P1 let's see. Okay. So we define a new ratio called pressure ratio. Pressure ratio. So pressure ratio is defined by P2 over P1. And we know P2 equals P3, P1 equals P4. So it will be the same as P3 over P4. Okay. So this is 1 minus this is RP, 1 over RP to K minus 1 over K, right? So this is 1 minus RP to K minus 1 over K. This is 1. Okay, so we got the thermal efficiency. Okay, so another new ratio you need to know is the pressure ratio. So in Otto cycle, now I think in all these 3 cycles, we have compression ratio. We didn't use the compression ratio in Brayton cycles, but we do use the compression ratio in Otto cycle and diesel cycle. And for diesel cycle, we have one more ratio called cutoff ratio, right? So compression ratio and cutoff ratio, they are volume ratios, but the pressure ratio here is literally pressure ratio. Okay. So don't get confused with these 3 ratios. Compression ratio, cutoff ratio, they are volume ratios. Pressure ratio is of course pressure ratio. Okay. All right, so this is something different from the Otto cycle and diesel cycle. Okay, so we have one more additional ratio to use, which is pressure ratio. Okay. All right. So the thermal efficiency of a Brayton cycle depends on the pressure ratio and, of course, the specific heat ratio. Okay. So look at this. The thermal efficiency of an ideal Brayton cycle depends on the pressure ratio of the gas turbine and the specific heat ratio, right? Pressure ratio is RP. Specific heat ratio, this is K. Okay. So as you can see, when the pressure ratio increases, then the efficiency increases as well. Okay. Of course, when the specific heat ratio increases, the efficiency increases as well. If you are talking about the same pressure ratio, if you want to change the specific heat ratio or vice versa, when you are talking about the pressure ratio increases, then the thermal efficiency increases. that also depends on the constant specific heat ratio, right? Because this is for a constant specific heat ratio, and this blue line is also another. Let's say this is K1, this is K2, things like this. This is K3. Okay, so K1, K2, K3, they are constants. Okay, so when the specific heat ratio increases, then the thermal efficiency increases. Saying this is based on the same compression ratio like this. Okay, based on the same compression ratio. So this efficiency is larger than this one. Okay. All right. However, so you know that let's see. So the highest temperature of the cycle occurs at the end of the combustion process. And this is limited by the maximum temperature that the turbine blades can withstand. Okay, so this also constrains the pressure ratios that can be used in the cycle. Okay, so let's go back to the video. What does this mean? I can stop this. Okay. All right. So let's go to here. All right. Okay. So this is the compression process. This section is compression process, and this section is the heat addition process. Okay. So you can see this heat addition process or the combustion process makes the end of the combustion process has the maximum temperature among the entire process. Okay, and look at this. Probably not very clear, but I think it's still visible. See this like gear stuff? Okay, there's a tiny blade like this. Okay, I clean this. Okay, so this is the turbine blade. Okay, so we know turbine blade is made of some kind of metal or metal alloy. Okay, so the maximum temperature is limited by the temperature that does not melt this turbine blade. Okay, so this is what the statement here says. Okay, the highest temperature in the cycle occurs at the end of the combustion process, and it's limited by the maximum temperature that the turbine blades can withstand. Okay, so this temperature at state 3 cannot be too high that to melt the turbine blades, or otherwise the entire device will be failed, right? Okay. So the pressure ratios are also constrained by this condition. So the maximum temperature cannot be higher than the temperature that the turbine blades can withstand. Okay, so if you fix the minimum temperature, which is usually room temperature, and the maximum, okay, on a TS diagram, so we know that the area enclosed by the process curves in a TS diagram or a PV diagram will be the same, right? Which is the net work out, because this is a Q in minus Q out. Okay, so the area enclosed in this case, this area is the net work out. Okay, so you can see if the temperature, the minimum and maximum temperature, they are fixed, then you can see the area enclosed by these three process curves will be different. And these three process curves represents the different pressure ratios. Okay, so like this pressure ratio is 2, this pressure ratio is 8.2, this pressure ratio is 15. So you can see the area enclosed by these three different pressure ratios made the process curve will be different. Okay, so this is pretty mouthful. So let's try this. So this area, let's say this is W1, and this area is W2, and let's try green. This area is W3. Okay, so you can see W2 would be larger than W1 and W3. Okay, so that implies that there's a optimum pressure ratio that can max the area maximum. Okay, so how do we get this? So basically, we have efficiency, right? When the efficiency is the maximum, that means the net work out is maximum, right? Efficiency and net work output, they are proportional with each other. So efficiency is maximum, that means the net work output is maximum. And we know we can write the efficiency in terms of the pressure ratio, okay, if the specific heat ratio is a constant. So all we can do, or all we need to do, we want to find out what RP makes the efficiency maximum, right? So what we need to do is to take the derivative and set it to 0, right? So it's the efficiency over the RP, we set this 0. So we know what is the optimum RP that makes the efficiency best. Okay, so by doing this, we can find this relation. So RP should be a function of course, maximum, minimum temperatures, as well as the specific heat ratio. Okay, all right. So let's try this example. A gas turbine power plant operating on an ideal Brayton cycle that has a pressure ratio of 8. The gas temperature is 300 K at the compressor inlet and 1300 K at the turbine inlet, utilizing the air standard assumptions. Okay, no code. It's just air standard assumptions. That implies that you will need to take the variation of the specific heat over the temperature into account. Okay, that also implies you will need to use the tables. Okay, all right. So we are looking for the gas temperature at the axis of the compressor and the turbine, and the backwork ratio thermal efficiency. So similar to the Otto cycle and diesel cycles, all we need to do is to get the pressure and temperature for every state. Okay. However, in this case, because the pressure information is unknown, so we are unable to get the pressure. We are unable to get the pressure of each state. Okay, so that's fine, because in this case, all we need to know is the temperature. Okay, so now T1 is known and T3 is known. Okay, they are given. So all we need to do is to get the T2 and T4. Okay, so let's try this. First, of course, you need to know that from this diagram, apparently 1 to 2 is isentropic compression. Okay, 1 to 2 is isentropic compression. And don't forget this, we are using just air standard assumptions. So for ideal gas with variable specific heats, we know that the pressure ratio will be the same as the relative pressure ratio. And relative pressure is a function of temperature only. So as long as you know the temperature, you know the relative pressure, or vice versa. As long as you know the relative pressure, you will be able to know the temperature. Okay. So 1 to 2 is isentropic process. So for isentropic process, the pressure ratio is the same as the relative pressure ratio. Okay. And the pressure ratio in this case is 8. This is 8. Okay. And T1 is known, so you know PR1. Okay. Because P1 is known. So you can use table A17 to get PR1. Okay. So we know PR2 or P2R, whatever, then you should be able to know T2. Okay. And similarly, P3 over P4, let me see, P3 over P4 is P3R over P4R. This is also 8, right? So you know T3 is 1300 K. So you know P3R. So you know P4R by doing this. So you know T4. Okay, right. Let's see. PV diagram, yeah. So P2 over P1 is the same as P3 over P4. Okay. P2 over P1, this is pressure ratio. P3 over P4, this is also pressure ratio. So we get T2 and T4. Okay. Then the back work ratio, is defined by the compressor work input over the turbine work output, right? So this is a compressor work input. This is the compressor work input. So this should be H2 minus H1. And turbine work out, this is turbine work out. So this should be H3 minus H4. And now you know T1, 300, T2 here, T3, 1300, and T4 right here. So you can use the table to get the enthalpies, because the enthalpy of an ideal gas depends on temperature only as well, just like the relative pressure. Okay, but here, make sure you use the table to get enthalpy. You cannot use the CP T2 minus T1. This is CP T3 minus T4. You cannot use this. Okay, you cannot use this because we need to take the variation of the specific heats over the temperature into account, because here we are using air standard assumptions, not cold air standard assumptions. Okay, so you cannot use this. Okay, so enthalpy depends on temperature only, so you can get all these for enthalpies. Okay, this is backward ratio. And thermal efficiency, all right, from the definition, just from the definition, this is the network output over the heat addition, right? Over, we can say this is 1 minus Q out over Q in. So this is 1 minus Q in is here. Q in is between process 2 to 3, and 2 to 3 is a constant pressure process. So Q out is H3 minus H2. Sorry, no, this is Q in. This is Q in. H3 minus H2. And Q out, this is Q out. So Q out is 4 to 1. 4 to 1 is a heat rejection, and it's also a constant pressure heat rejection. So this should be H4 minus H1. Okay, so then you can have the thermal efficiency. Okay. Questions about this one?
Professor, in this case,
Yeah.
how do you find P3R? P3R. How do we know P3R?
Relative pressure depends on temperature for an ideal gas. Okay, so if you go to the table A17, just go to A17 right here. So PR, relative pressure, depends on temperature. So once you know the temperature, you know the relative pressure, or vice versa. Once you know the pressure, once you know the relative pressure, you know the temperature using the table here. Okay.
Okay.
Any other questions? All right. Then let's look at this. Air has its own significance and functions in gas turbines. One is to supply the necessary oxidant for the combustion of the fuel, and serves as a coolant to keep the temperature of various components within safe limits. And another thing for air is draws more air than is needed for the complete combustion of the fuel. So that's why air is very important in a gas turbine engine. Okay. Then in a gas turbine engine, treating the combustion gases as air does not cause significant error, because the air-fuel mixture ratio is usually greater than 50. So that means 50 air to 1 fuel. Okay, so because this ratio is just too big, so we can just treat the air-fuel mixture just like air. Okay. So compared to steam turbines and diesel propulsion systems, the gas turbine offers greater power for a given size and weight, high reliability, long life, and more convenient operation. We didn't talk about anything about steam turbines. This is part of chapter 10, okay? And yeah, we didn't talk about diesel propulsion as well. But here, just to let you know that the advantages of a gas turbine is offering greater power for a given size and weight, and it's usually very reliable, long life, and very convenient to operate. Okay, and the engine start engine start time has been reduced from 4 hours required for a typical steam propulsion system to less than 2 minutes for a gas turbine. So the startup time for a gas turbine is relatively short compared with a steam turbine. Okay, and for the advantage of this, offers greater power of a given size and weight. So this is also the reason why that the gas turbine engines is just like the jet engine. Okay, so we want to make an airplane fly. So we are not going to use the steam turbine engine on an airplane because steam turbine engine is usually very big, very heavy, and the start time is 4 hours. You don't want to wait 4 hours to wait an airplane to be started, right? So this is one good thing about gas turbine engines. Okay. All right. Next is the deviation of actual gas turbine cycles from ideal ones. Okay. From chapter 7, we have learned isentropic efficiency. So isentropic efficiency is used to evaluate the deviation of actual device from the ideal one, right? So we have been evaluated the turbine and compressor, and these two devices are like happening to be here for the gas turbine engines. Okay. So basically we can combine the isentropic efficiency problem with the gas turbine engine problems or gas turbine cycle problems. Okay. So here, the actual gas turbine cycles differs from the ideal Brayton cycle on several accounts. One is some pressure drops during the heat addition and heat rejection processes is not avoidable. Okay, so that means in the real situation, in real practice, there must be some pressure drop when the working fluid is transferring or is transported around the pipes, around or in the pipelines. Okay. Then the actual work output to the compressor, it's more, right? This is what the isentropic efficiency tells us, right? The real one is not going to be reversible. Okay, the real devices are always irreversible. So the actual work input to the compressor is more than the work input to an ideal compressor, right? Another thing is the actual work output from the turbine is less, right? Because of the irreversibilities, right? So the isentropic efficiency of a turbine is the net work out of a turbine. This is also net work out of the turbine. And the isentropic one, this is the actual one, right? So that would be H in minus H out. This is H in minus H out, right? And we don't change the inlet condition, right? We just change the outlet condition. So this is the actual one. This is the isentropic one, right? For compressor, this is the work input, isentropic one. This is the actual one, because for a compressor, the actual work input to the compressor is more than the ideal work input to the compressor, right? So by doing this, we can ensure that the efficiency is lower than 1, right? And this is H, this should be H out minus H in, right? The H out minus H in. So this is S, this is A. Okay. So this is what we learned in chapter 7. Okay, isentropic efficiency for turbine and for compressor. Yeah, so just like this, the isentropic efficiency. This is isentropic efficiency. Isentropic efficiency. This is also isentropic efficiency. One for compressor, the other one for turbine. Okay, so on a TS diagram, so the isentropic one, this is isentropic compression. This is 2S. So 2S is, so S1 is the same as S2S, right? But the actual one will be a little bit different from the isentropic one. So this is 2A. Okay. So the process curves on a TS diagram will be a little bit off from the ideal one. Okay. All right. So let's try this one. So this example is kind of a follow-up from the example last one, from last example. Okay. So this example, this is an ideal case, ideal Brayton cycle. So 1, 2, 3, 4, 1 to 2, 3 to 4, they are isentropic. So this T2 and this T4 is actually T2S and T4S. Okay. Again, look at this. So this is isentropic compression. So state one is the inlet of the compressor, and 2 here is the outlet of the compressor. Similarly for 3 to 4. 3 to 4 is 3 to 4 is the isentropic expansion. So this is an isentropic turbine. So 3 is the turbine inlet, 4 is turbine outlet. Okay. So again, for isentropic efficiency, we don't change the inlet condition. We just change the outlet condition. So that's why this is 2S, this is 4S, because 2 is the outlet of the compressor. 4 is the outlet of the turbine. Okay. So this one says that assuming a compressor efficiency of 80% and turbine efficiency of 85%, we're looking for the backwork ratio. So let's deal with the compressor efficiency first. So the compressor efficiency, let's say efficiency compressor, we know this is the work in over work in, but the isentropic one, the real one, the actual one. So this is H2 minus H1. This is H2 minus H1. So this is isentropic one, this is actual one. So this is 80%. So this is 0.8. Okay. So we know all this. This H2S is because again, enthalpy depends on temperature only, right? So T2S is known from example 9.5, from the previous example. We know T2S, right? So you know H2A, so that you know T2A. Okay, you know T2A. Similarly, for turbine, it should be the actual one over the isentropic one, right? So that would be H3 minus H4, H3 minus H4, S, this is A, okay. So T3 is known, so these are known, and sorry, H4S is known because we know T4S from the previous example, okay, and this is 0.85. This is 0.85, okay, it's turbine efficiency, right? So we know H4A, so we can know T4A, okay? Then the back work ratio, just follow the definition. So the back work ratio is the turbine output, and here is the compressor input, okay? So the compressor input is H2A minus H1. The turbine work out is H3 minus H4 A. Okay. So you have all this. You have all this. Okay. You know this, and H1, H3, because T1 and T3 are given. So you can use the table to get H1 and H3. Okay. The back work ratio and thermal efficiency. Well, just follow the definition. Thermal efficiency 1 minus Q out over Q in. So this is 1 minus Q out. Okay. Now Q out is 4A minus 1. So this should be H4A minus H1. And Q in is H3 minus H2A. Okay, this is Q in. So it's H3 minus H2A. Okay. Then turbine exit temperature. Turbine exit temperature. This is T4A. This is T4A. So that's it. Okay. So no matter, well, we start from the ideal case first. Then if this is the case, just follow the definition for the isentropic efficiency. And in this case, we are dealing with the isentropic efficiency for compressor and turbine. Okay. All right. Questions? If no, then this is all we need to cover. Okay, so the final exam covers all the way here. So chapter 6, chapter 7, then chapter 9 until this example. Okay.